are from Chemtech Research Team.
Hello, my name is Ahmed Daniel.
And my name is Muhammad Faiz Daniel.
My name is Alia Nisara.
My name is Rashidi Nisha.
My name is Normatura Famugani.
My name is Sharmila Finish.
Finally, my name is Dylan Axel. Okay, we have a new project coming in. Okay, Squadron has been imported from the exoplanet to the Chemtech Research Park in Japan. Okay, generally, Squadron is a drone to transport sample from one location to another. In this project, it will be transporting sample from Block A to Block B with a distance of 3.2 km and a total of 6.4 in two-way transportation. Okay, the activation of energy of this reaction is 36 kJ per mole without a catalyst, but with a catalyst it can be reduced until 20 kJ per mole. Upon adding the catalyst, we can achieve 10 km per hour for the speed of the drone.
If that's the case, let's start with the sampling of the case. In Japan, there are 4 distinct seasons, which are summer 27 degrees Celsius, fall 25 degrees Celsius, spring 21 degrees Celsius, and winter 10 degrees Celsius.
Wow, so impressive. So how does the squadron actually work?
Okay, working principle of the squadron is actually simple. To elaborate, this squadron fuel hydrogen peroxide, produce a thrust force to propel the drone and to the intended location. When this H2O2 or hydrogen peroxide is subjected to the decomposition reaction, oxygen and water are produced, and this produces enough thrust force to propel to move to object. The pace of H2O2 decomposition reaction is impacted by the seasonal fluctuation in the environmental temperature. Throughout the experiment, we presume that pressure in this case is negligible.
Alright, since you are talking about concentration, let's discuss further about chemical kinetics, specifically for hydrogen peroxide. Okay, concentration of hydrogen peroxide has significant effect to its decomposition rate. Generally, an increase in concentration of hydrogen peroxide leads to a faster decomposition rate. This can be explained by collision theory in chemical kinetics. Collision theory, for a reaction to occur, particles must collide with sufficient energy and proper orientation. In the case of decomposition of hydrogen peroxide, the higher the concentration, the greater the number of hydrogen peroxide molecules present in each volume. As a result, there is an increase of probability of collision between hydrogen peroxide molecules, leading to a higher frequency of effective collision. Okay, this means that more hydrogen peroxide molecules possesses the necessary energy and orientation to break the single bond and initiate the decomposition reaction. Consequently, the rate of the reaction increases. However, at extremely high concentration, the reaction may reach a maximum value due to factors such as overcrowding of molecules and increased intermolecular forces that can hinder the collisions and slow down the reaction. In summary, the concentration of hydrogen peroxide influences the rate of its decomposition. The higher the concentration of hydrogen peroxide, the higher the rate of reaction.
Then, a catalyst must play a role here. A catalyst is a substance that increases the rate of chemical reaction without being consumed in the process. In the case of decomposition of hydrogen peroxide, certain catalysts can significantly affect the reaction rate by providing an alternative pathway with lowering activation energy. Activation energy is the energy threshold that molecule must overcome for a reaction to proceed. By reducing this energy barrier, more hydrogen peroxide molecule can overcome the activation energy and precipitate in this reaction. As a result, the rate of reaction increases. Common catalysts for the decomposition of hydrogen peroxide include substances like manganese and potassium iodide or enzymes such as catalase. In summary, catalysts accelerate the decomposition of hydrogen peroxide by lowering the activation energy and increasing the frequency collision.
This is quite interesting. Let's discuss further.
Okay, a
upon the discussion, we managed to figure out our problem statement and objective to the smaller scope. The first problem is duration of the total time travel is not provided. Therefore, the total time traveled by the squadron for two-way transportation need to be determined. The second problem is at 4 different seasons. The first one being to determine the optimum operational duration of squadron, and the second to determine the optimum initial concentration of hydrogen peroxide at 4 different seasons.
In order to get optimum time, we are going to use speed equal to distance over time, and we will be going to get 38.4 minutes. The second part, here are the formula used.
Since we all know that the rate of reaction varies for each reaction and change quite often, isn't it better for us to identify the factors affecting the rate of reaction first?
These are the 4 factors that affect the rate of reaction.
Let's look at the experimental data that we have obtained from the experiment. It is important to note that the graph is only applicable for the first and second order of the reaction. 2 graphs has been plotted again to differentiate between the first order and the second order. An interesting observation has been observed as the graph exhibits a linear relationship. Through analysis, it has been established that the graph follows a first order reaction, as evidenced by the straight line nature of the data. However, we still tried it out for the second order. Notably, the resulting graph exhibits a curved shape that does not fully meet the criteria for a second order of the reaction. As a conclusion, the first order reaction meets all of the requirements upon plotting a graph, and therefore this reaction is a first order reaction.
By using Arrhenius equation, we could get K for 4 seasons. The first one, 3.918 to the power of negative 4. The second one, summer, 4.2017 to the power of negative 4. The third one, spring, 3.568 to the power of negative 4. And the last one, for the winter, will be 2.5968 to the power of negative 4.
The proposed concentration of hydrogen peroxide against time is as follows. The rate constant for the first season, summer, is 4.2017 exponent negative 4 per second. Therefore, the squadron initial hydrogen peroxide concentration requirement for the summer is 0.012 molar. Next, the rate constant for autumn are 3.9818 exponent negative 4 per second. Autumn starting hydrogen peroxide concentration content is 0.0114 molar. Other than that, the rate constant for the spring season is 3.569 exponent negative 4 per second. The initial hydrogen peroxide concentration is therefore 0.0104 molar. Last but not least, the rate constant for the final season, winter, is 2.5968 exponent negative 4 per second. And consequently, the starting hydrogen peroxide concentration for the winter season is 0.0083 molar. From the table, it can be seen that as the temperature increases, the rate constant will also increase. Subsequently, the initial hydrogen peroxide concentration needed increase together with the rate constant.
Okay, despite conducting the experiment and calculation till the last decimal place, there are still some limitations in the experiment, which are the kinetic and thermodynamic limitation. Kinetic and thermodynamic limitation refers to the factors that can influence or inhibit the natural behaviors of a chemical reaction. From here onwards, the definition behind each of these limitations and a few factors that could contribute to them will be discussed.
On, the kinetic limitation in this study will be discussed. Kinetic limitation refer to the study of the reaction and the factor that influence them. These factors include:
At the end of the experiment, it has been verified that the objectives stated are achievable.
the total time and distance between block A and block B in the two-way transportation has been successfully identified.
Moreover, the initial concentration of hydrogen peroxide that we use in each region has been calculated and measured.
The optimum initial concentration of hydrogen peroxide in summer, fall, spring and winter are 0.012 molar, 0.0114 molar, 0.014 molar and 0.0083 molar respectively.
Throughout the project, all factors like activation energy, minimum working concentration of the squadron, which is 0.004 molarity, the temperature changes in each season, and the kinetic and thermodynamic limitation has been confirmed.
To ensure accurate and precise result measure to overcome the kinetic and thermodynamic, limitations are taken into account by controlling the reaction conditions such as temperature, concentration, and catalyst usage.
For overall, it is a successful project by a Chemtech research team.